Hi there, guys. Here's my solution to question 9.56. A study of rush hour traffic in San Francisco counts the number of people in each car entering a freeway at a suburban interchange. Suppose that this count has a mean of 1.5 people, there it is, and a standard deviation of 0.75 in the population of all cars that enter this interchange during rush hour. So part A, could the exact distribution of the count be normal? Why or why not? And the answer is no. X can't be exactly normal. And essentially what's going on here, X is a count. You have to have at least one person in the car. Someone has to be driving. There could be 2 or 3 or 4 or 5. We could list all of these outcomes, but they are discrete. X can't be normal because a normal random variable is continuous, and X is not a continuous random variable, it is discrete. So that's the fundamental issue here. However, in part B, X bar can be represented with the normal distribution. So apparently the capacity of the interchange is 700 cars per hour. So by the central limit theorem, what is the approximate distribution of the mean number of persons, X bar, in 700 randomly selected cars at this interchange? So fine, the mean can be determined as normally distributed. The average needs to be the true average of 1.5. That was given to us. But now the standard deviation of the means is the standard deviation of the population, but divided by the square root of our very large sample size. So this expression simplifies to about 0.028. So, but this is true under two conditions. Number one, I need independence. So if I take 10 times my sample size, that gives me 7,000. That needs to be less than or equal to the number of cars entering the freeway in total from this population, especially if this is a particularly busy interchange. I have no problem with believing that that condition is satisfied. Then the normality condition here, and this is true by the central limit theorem, 700 is certainly a large sample. This is greater than or equal to 30. So we can believe that our sample means are approximately normal by the central limit theorem. So lastly then, in part C, we're trying to find what is the probability that 700 randomly selected cars will carry more than 1,075 people through this interchange. So there is the event that we are trying to describe. The total number of people in 700 cars, what is the likelihood that that is greater than 1,075? So in part B, we found the distribution of the sample mean, so it would be good to use that distribution in this case. That's certainly what the hint is suggesting. So on the left side here, we have a total in 700 cars. So all we really need to do is take both sides of this inequality and divide by 700. So what that will do, the total number of persons in 700 cars divided by 700, that's turned this question into a question about the sample mean. 1,075 divided by 700, that's approximately 1.536. So we can think of this question as now, what is the probability that the mean, that the average number of individuals in these 700 cars is greater than 1.536? That's the condition that would be required in order to get the total of these 700 cars to be more than 1,075. So of course we know we can use the normal distribution here. I know the mean and the standard deviation. We've already calculated that. So my z-score then, I can convert this into a probability involving z-scores. So from x bars to z-scores, I can take my actual value that I'm interested in, the 1.536, subtract the mean, divide by the standard deviation. So now we need to calculate that. We'll go to our calculator here. So as a z-score goes, I'll take the 1.536. I will subtract the 1.5. Close my parentheses. There's my deviation. And I'll divide by 0.028 to standardize it. So I've got a z-score of we'll call it 1.286. So I think it's good to consider the picture in this context also. So what we've got here, and we could write this picture in terms of x. We could write this picture in terms of z-scores. I'm going to draw it in terms of z-scores. So our z-scores have a mean of 0. They have a standard deviation of 1. And I'm interested in z-scores that are at or essentially more extreme than 1.286. So that's going to be out here. I will label this as z equals 1.286. And I am interested in this probability here represented by this shaded area. So of course that shaded area is above the 1.286. So if we're going to use the normal CDF command to do this, this is the lower boundary, and I need to be able to use z-scores high enough that it will capture this area in an accurate way. I advise you to use a z-score of 10. So here's my lower boundary, and here's my upper boundary. So again, we can go back to the calculator to calculate this. I strongly encourage you to use the normal CDF command rather than using the shade norm command, but you are welcome to use the shade norm command if you want to. Just make sure that you have the correct window set, turn off your stat plots, and make sure you've cleared the drawing. I'm just going to go straight to second variables. There's normal CDF. So my lower boundary is the 1.286 that I found. And then we'll go down to the upper boundary. That is positive 10. Of course, we're using z-scores, so the mean of 0 and standard deviation of 1 we don't have to mess with. There we go. So the likelihood is around, we'll call it 0.10, 0.099. So basically 1 in 10. There we go. So to review, this is a question then about sample means. So in part B, we described the sampling distribution of x bar. We described its shape. We described its center. We described its spread. And we had two conditions to consider. We had the independence condition to consider. So we want our population to be more than 10 times the sample size. We also had normality to consider, and since we have a large sample size by the central limit theorem, we can use normality. So then what I believe is the most challenging part of the question is in part C to try to take the event that's being described and convert it into an event about x bar where we can use the sampling distribution to actually come up with this probability. So once I was able to convert this into a question about the sample mean, then I can create a z-score. I can make a picture to represent that probability we're about to calculate. We can use a shade norm command, or we could use my preference, the normal CDF command, in order to calculate that. Hope this has been helpful.